Hi, welcome to yet another video from the channel Limitless Tech. So, 4 years ago, Apple made a transition from the generic Intel CPUs to their custom-baked M-series CPUs. And this has since set the benchmark for computing in the industry. Until a couple weeks back where the Snapdragon X Elite processors was tested on individual PCs. And it was noted that this was the Apple moment, at least for Windows. When I was trying to wrap my head around these possibilities of technology in modern day, I came up with more questions than answers, and the bigger question being ARM. Because in those single reviews and articles that I read, just ARM had to be mentioned someplace, somewhere. So I went into research, I went into documentation, I dedicated my time just trying to figure out, just trying to wrap my head around what exactly is ARM. And boy, is it interesting. And there are interesting stories and videos like from a good friend of mine, John Coogan, that I've linked below the description, which all try to explain what exactly is ARM in modern computing. But my version of the story is interesting, and it starts with a story. ENIAC, the world's first digital multi-purpose computer built in the mid-40s that will do up to 5,000 calculations per second. This was ridiculous in context, considering that prior to that, a computer was defined as a bunch of people that sit in a room with a pen and paper performing calculations. These calculations could take up to a single day performing a single one, considering the complexity of the calculations. But impressive as it was, this, however, lacked in many different aspects. For starters, it took up a huge amount of space, like 1,800 feet, and it drew a huge amount of power and produced great amount of heat, so great that it needed its own air conditioning system. Up to ENIAC, it was clear that computers were the future, but the limiting factors of ENIAC weren't exactly the future. We're not here for a history lesson, but if we want to understand the computer architecture, which is the fundamentals for this video, we need to understand how the first computer, ENIAC, was operated. And for starters, the basic 4 steps of operating this computer were as follows. First, you had to code manually. Then you had to calibrate the computer to see if it primarily functions, because it was basically made of light bulbs that needed replacing once or twice. So you need to calibrate that before loading the code. Then, third step, you had to actually load the code via a manually tiling process. And for starters, it took up to a single day writing a single program on that first computer. And finally, documenting and output validation. So as basic as these steps were, and as manually involving and as manually demanding as this process were, these later on were to build the foundation of computer architecture. So, following the first computer ENIAC, a mathematician, John von Neumann, drew a pivotal line of what was to be later the fundamentals of computer architecture, or to put it in context, the first known computer architecture, the von Neumann architecture, or simply the fetch, decode, execute cycle. That still is the first thing you need to learn when pursuing courses like computer science. Now, computer architecture literally defines how the core computer peripherals are able to exchange information and communicate between one another. Now, these core computer peripherals are the main CPU components, that is the control unit, the arithmetic log unit, and the registers. Now, to understand computer architecture, visualize it as a circuit that is laid or drawn somewhere. Now, this circuit is a rough representation of how these electrons flow from a point A to point B in that loop of a circuit. Though it's drawn on a hand, it greatly impacts how the final product is going to behave. And that was the basic concept of computer architecture. But believe me, it's way more complex than the way I put it there. But for the sake of, improving efficiency and lengthening this video, that was the basic computer architecture. There are numerous kinds of computer architecture, but for today, we'll talk mainly on the one that brought us here in the first place, the instruction set architecture, or simply ISA. Now, understanding ISA needs us to have the basic knowledge of the core computer peripherals, which luckily we did explain down the length of the video. So, these components communicate with each other in a set of instruction sets. Think of these instructions as a calculation that you're supposed to do. The calculation can be a simple 2 plus 2, which can be solved and can be enumerated to the answer 4, but can take 2 different turns of completing that task or that calculation. The first, you can be the first grader as you are and count up your fingers to 4, 1, 2, 3, 4. And the other end will involve you dealing with complex numbers, calculations, logarithms, and so forth, just rounding to the nearest 4. So those 2 options give the answer 4, but from 2 opposite ends of the spectrum. And that was a brief introduction on the types of ISA. The first is reduced instruction set, and the second is complex instruction set. And of course, the C there stands for computing. From our mere simple example that we explained earlier, think of RISC as the first grader that takes things simply. Yeah, boy. Just does the calculation simply and effectively within no time, the answer, boom, is 4. But think of CISC as the second guy who is in a higher level. Though his calculations are technically better than the first grader, his calculations draw up more power and efficiency. Since we're talking of ARM, from the entire time of ENIAC, the mother of computers, the only predominant instruction set that existed at that point was CISC, and RISC was just an engineering marvel written theoretically down a paper. This was so until a bunch of clever engineers and some really good funding came from the joint of 3 companies. Apple, yes, the Apple that you know today, Acorn Computers, and VLSI Technologies. This venture then made the birth of advanced RISC machines, ARM. Before that, ARM was a standalone company that built its own processors. But from this venture, ARM was born that we know of today, a company licensing computer architecture. In the computing world, this was rather a very great venture to have taken place in history, because the next years after this venture, we saw the introduction of portable devices that were centric on performance, that were centric on efficiency, like the Nokia 3310s. For those people who are, old and mighty, you remember those devices. Now, those devices, some that needed efficiency and performance at the same time, were basically running an ARM instruction set architecture of some way or some kind. Through this joint venture, what was once thought impossible by most companies and most engineers became possible. In fact, the first computers, the first chips that were made by this venture of Apple, Acorn Computers, and VLSI Technologies, their first chips did so well that in fact when they were cross-checked, it was found that they were running on the leakage current. And if you're anyone that knows anything about electronics, leakage current is always considered negligible in those circuits. So them making a chip, the first generation of chip that was once thought impossible, that not only was efficient but ran on leakage current. I mean, you gotta respect what effort was put in crafting the ARM architecture that we know that is existent today. But not everyone could make a breakthrough of such kind, considering things like the funds and the engineering brains of even doing that. But they could at least have a piece of cake. And here comes one aspect that I think is most misunderstood by people, at least it was misunderstood by me. Licensing. This meant that advanced risk machines, ARM, could not sell the exact chips, but they could sell the architecture. John Coogan put it this way: the architecture is like a recipe that you as a chef are meant to, cook some food out of it. Now, the recipe can come with those default ingredients, but that doesn't mean that you cannot add individual ingredients to customize the recipe and make the food much more customizable. That is exactly what ARM is doing, licensing their recipe to other manufacturers like Qualcomm, like Intel, like AMD, so that they can not make this exact chip, but they can at least use that architecture to build their custom baked, more powerful, more efficient, more energy saving chips, but still be on that foundation of ARM architecture. Since the late 80s, ARM got its place on the computing map, but still was used on most low-power devices like mobile phones, and still couldn't be integrated on those high-end devices like PCs and desktops. This made ARM popular, but not on the high-end performance models like the laptops or the desktops, but more on the smartphones that we carry daily. I mean, the LG Style3, which I reviewed earlier, runs a Snapdragon SoC that's based on ARM architecture. So you see, though ARM was great, it still had some things to be tweaked. It still couldn't be connected those official dots to make it be used in those high-end devices. Until the year 2020, where Apple made that last dot by connecting ARM architecture and moving from the common x86 process to their custom-baked M-series CPUs. This transition just meant that Apple was basically shifting from the CISC instruction set to the RISC instruction set, and they implemented it so well that most reviewers praised this shift on these generations of M series. This integration made by Apple on their Mac devices was so great that everybody knew that ARM architecture was the way to go if you want to beat that benchmark that Apple set there. And a few weeks back, yes, Qualcomm unveiled the Snapdragon X Elite, that Apple moment for Windows PCs. This didn't mean that ARM never existed on PCs, it did, but ARM wasn't existent the way that the Snapdragon X Elite existed now, translating to greater performance, translating to greater battery life, translating to overall user experience and longevity in their daily use. I hope by now you've understood at least the basic fundamentals of ARM architecture and how it's revolutionizing computing in general, how it's shaping us towards that great world of computing that we dream of. And since computing is getting in places that we never imagined, like in the Mac that I'm using right now, it's safe to say that ARM is basically in every way. Wherever there is a computing, there will be ARM. That iconic term I think I've understood from research and making this video, which I definitely had fun making. But until next time, I was your host Luke, and as always, the only limit is your imagination.